Okay, so yeah, so we saw how to take samples from a uniform and convert them to any other random variable using very specific formulae for inverting the distribution function. So I think the next, yeah, so we saw this for continuous ones as well, and uniform theta 1, theta 2, and let's see. Yeah. So, oh yes. So this is the exponential random variable is where we want to start it. So the next random variable is the exponential random variable. What is this guy? It's the one I wrote down on the board. It's density. It has parameter lambda after the semicolon, and it's the density where given by lambda e to the minus lambda x for every non-negative value of x. So that's the realizations of the random variable. And then lambda itself, the parameter has to be strictly greater than 0. Okay, so this is called the rate parameter. And its distribution function, by integrating that from negative infinity to x or positive x, it's 1 minus e to the minus lambda x. So that's straightforward to invert. And those of you who worked on Poisson distributions know that it's constructed typically from the inter-arrival time between events. So Poisson distribution counts the number of events occurring in a given unit of time according to some rate. And the way you construct a Poisson typically is by allowing the inter-arrival times between events to be exponentially distributed with the same rate parameter lambda. So it's like your typical first stop on traffic modeling and so on. And downstairs there is a U-try, a simulation for you to do a slightly complicated simulation where people are waiting in the bus and the bus has a given number of seats and the seats get filled up and the seats are filled up, you're not allowed to get into the bus. So you have to model, like do a little simulation in the end later. That's a good assignment for you to show me that you've done some work. So let's do this. So let's say x is 3, and we know that we can take the exponential by exp of x. Now I'm going to define the PDF and CDF, the formula you saw upstairs. And let's do a quick interact. So here's the PDF and CDF. So as I did on the blackboard last time, if I increase the rate parameter lambda, you see it's getting spikier towards 0, right? So that's how the rate parameter works. So if I make it very, oops, negative is not defined. So if I make it smaller, then you see it spreads itself out. This continues to positive infinity. So that's the general behavior of the PDF and CDF. So inversion is actually not that hard. You just have to set up a very simple equation like this. So always to solve for capital F of x, here's your basic equation. You set up u, the uniform number u in the 0, 1, equals the distribution function, and then you simply solve for x, right? Because you want to go the other way. So you simply solve for x in terms of u, and then you can get only an expression involving u on the right. So then when you plug in a uniform sample, voila, you get the sample from the distribution function, from the random variables distribution function as f. So for us, it's minus 1 over lambda natural logarithm of 1 minus u. Because, yeah. Okay, so natural logarithm basically has base as e. So here is the mechanics, the pseudocode. So it's exactly the same recipe. You pump in u and you get x from the exponential lambda distribution by simply using this 1 subtraction or 1 multiplication by minus 1, 1 division, 1 more subtraction, and the multiplication and the logarithm. So that's pretty easy peasy. So this is just implemented in the exponential f inverse here. And it's just the same exact idea. So we can produce n samples, and these are your samples already. You've set your lambda, the parameter you want, to be 0.5. So in this case, you're simulating samples from that lambda, and then you sample size n, and there comes your samples. So in this interact, we are just basically getting lambda, and we are simply, as 0.5, and we can play with the sample size and the number of bins. So if I have 2,039 samples and maybe 200 and maybe a little more, so you can start seeing that the normalized histogram should start hugging the PDF, basically. I mean, up to making the number of bins just right and stuff. And I already told you that's actually technically it's an open problem in mathematical statistics, how to get the right bins for a given n. Okay? So is that clear so far? It's just wham bam, nothing magic going on. So now we're going to introduce ourselves to this peculiar continuous random variable called the standard Cauchy random variable. And this guy is interesting because it has this following PDF. So f of x is 1 over pi 1 plus x squared. And x takes the entire values in the entire real line, right? And its distribution function is involves inverse tangent, right? So what's unique about this guy is its expectation does not exist compared to everything else we've seen. What does it mean for the expectation not to exist? What is the expectation of a random variable? Okay, so we're going to just take a tiny break for 1 minute into the board. So what is the expectation of a random variable by definition? For a continuous random variable? Yeah, you two can go to sleep. No. What is the definition of the expectation of a random variable?
It's the integral over the distribution. So the value
of the density function?
Yes.
Yeah, sure. You can do it this way. Of the value itself, right?
Yeah, times.
Yeah, so this is how we did this generally.
Yeah.
But for a probability density, a continuous random variable, it's this, right? Okay, so what do we say when we say the expectation does not exist? So when we try to evaluate this integral, we run into problems, right? We run into various forms. So in this case, this is what happens. So we have to take the integral of the absolute value of x and make sure that this is finite. Okay, so then the integral is well defined and the expectation exists. So for Cauchy it doesn't. So the point is you can have random variables that will have undefined expectations. Okay, so in Sage Math we can use the arctan function for tan inverse and pi for the usual stuff, and this is how we would implement the PDF and CDF of Cauchy. Right? So let's see. Do I give you guys a construction yet? No. So let's actually do this little interact and check out the shapes. So this is how the it's symmetric about the origin, right? And this is kind of how it looks. I mean, it looks harmless, right? It looks like Gaussian, but it's not like dying fast enough. Okay.
So the reason the expectation does not exist is because of the tails, or I mean, how should we?
Well, it's just I mean, if you evaluate this, you get infinity.
Yeah. But if you look at it, you could say sort of 0 seems to be the.
Yeah. That's still the median of the distribution, but the mean, the population median is 0, but the population mean is undefined. I mean, it's right. So that's kind of the point. And this guy is going to be our counterexample of all these famous theorems, because the theorems don't work for us when the expectations don't exist, right? And see, it's nice. And to kind of construct this is my favorite construction. So it's sort of Kiwi nerd construction. So, have you guys seen Darth Maul in Star Wars?
Yeah.
Yeah, yes. That's it. So, let's see. So, I think I'm still on the blackboard. Yeah, so basically what we're going to do is this kind of construction. So we place a double-edged lightsaber of Darth Maul, yes, it comes out on both sides. So basically you place it at 1, 0, I think. So this is where he grips it, and then imagine this lightsaber has infinite laser beam shooting out, right? So then all you do is you come here and then you play sort of roulette wheel. You give it a spin at random and let it come to rest, okay? So it's going to come to rest somewhere, right? And the chance that it's going to be exactly parallel to this is 0. So it's going to hit either somewhere on the upstairs or downstairs, right? It's going to intersect with this. So let's say, let me say I spun this and then it came to a rest like this position. Then it's going to intersect it here, right? That's going to be my sample X from Cauchy. That's Cauchy construction. That's how all the everything comes around. You can trigonometrically understand this. So you basically produce this spin angle between 0 to 2 pi, and then you can essentially get the y value. This is how the picture looks, right? Anyway, so simulating from the Cauchy, thanks to inverse time, we don't need to do all this. So we basically solve for x. This is the usual recipe, right? We set the distribution function equal to u and solve for x in terms of u. And then we basically get x's tangent of u minus half times pi. So this is just mechanical step-by-step high school maths. This is high school maths, right? That's what I said, prerequisite for the courses. Okay, so inversion sampler for the standard Cauchy random variable is basically exactly implementing that little formula the usual way. So here's Cauchy F inverse and Cauchy sample, and then let's try and interact with this. I think I'm missing an interact or something. I don't know what happened. What do I do? At interact? It's going to be busted. Oh, yeah.
Isn't it just one? Oh, no.
No, I think I don't know. I was like, I don't know. I was writing all the notebooks simultaneously, so there may be busted things we can fix. So you just add this at interact. It's really trivial. You can make interacts yourself if you want. You just have to add this, and then there's some little magic, which is obvious syntactic structures for getting these bars and stuff. So there we go. We have 50 standard samples. I'm just showing you the sample ID in the x-axis. And but the point is, you see a lot of them are concentrated here because it's standard Cauchy. But the point is these things that lie far away, like 476 and minus 436, those things keep happening. They're not like super rare events. They are. Because you just need something like, something super close to infinity once in a million years, right? Like if you have a near extinction event, boom, it's like, So it's kind of like that, right? So here is so here's just basically the histogram way of looking at the samples, right? So it looks, so if you just increase the sample size and make the bin size somewhat reasonable, let's see. So you'll start seeing this number should keep, so I'm also controlling this lower and upper, which is annoying. So so we won't really see the really rare ones, but they keep occurring, okay? Okay, so the next main concept is running means. So we can now start seeing, so if I have samples and I take the first k of them and sum them, divide by k, that's my sort of mean up to the kth one. And then I take the next one and update the mean, right, and so on. So that becomes my basically my cumulative sum function, remember, divided by the current sample size. So it's called the running mean. So if we look at the running mean of a sample simulated from Cauchy versus the uniform 010, then we will sort of start seeing some interesting patterns, right? So here I'm just producing a sample from the uniform, just 10 of them. And this is just explaining the concept of a running mean. Too slowly, but yeah, you basically, you just take the cumulative sum and divide by the sample size. So that's what we're doing here. Take the cumulative sum. So now you can see the cumulative sum is growing, and we simply divide by the sample size like this. So that's the running mean. So we get our sample size, and then we do a nice simple list comprehension. Yes. Almost have this fancy monitor now in my house. Like this TV thinks everything becomes weird. I mean, it's nice to see, but it looks like the lines are so long. So I have all these broken lines now. Okay, so that's basically my running mean. And it seems like it's kind of seems to have a little pattern. It starts around 5 and starts oscillating around 7 point something. Just for 10 even. Okay, so now let's pull this all together and put this in the function. Okay, how we can reuse this. So there's a function to give a list of n running means from uniform theta 1, theta 2 random variable. And then we can just plot this. So it's just the same thing we're seeing. So if we increase the sample size, let's see what happens. Now, 1,000 samples. And I'm doing multiple simulations now. So each one is simulated, each one is a running mean with a different, seed or different subset of the sequence of pseudo-random numbers. So what's the point? The point is, in each of these 5 simulations of the running mean, they start oscillating, but note that they all converge to something. Right? So what are they converging to? 5? Yeah, it looks like it. So 5 must be in the middle of this thing, right? I don't know. Is that right? What is theta 1 and theta 2? 0 and 10. Oh. Okay. So we'll revisit this idea more closely using notions of convergence and probability and Poisson distribution. So this is a you try. Your task is now to do the same thing for some standard Cauchy running means, right? So you can basically modify the code, and if you have plenty of time, I'll let you guys play with this for about 10 minutes and look around, but don't have time. So you will see, we'll revisit this, you'll see that for the Cauchy, the running means are going to have very different behavior. Can you guys guess what say I do 5 simulations of Cauchy running means, samples from Cauchy. What do you think will happen as time goes on? Huh?
They will keep
Yeah, so I don't think they'll come to any point, right? I mean, they won't all agree because there is no mean. So they will all do their own thing, depending on where Dartmouth's lightsaber land. They will jump like crazily from one side to the other. So it's actually cute to watch. Yeah, so they'll keep oscillating basically. Okay, so yeah, that's a good. Oh, sorry. Oh yeah, you're supposed to fill this part. So I haven't done anything, but if you go and play around, it'd be good exercise. So there's a bit about replicable samples. So So, you know, we already talked about random, which is our pseudo-random number generator built in, and then the set random seed function. So what we want to do is be able to, you know, just be aware of this, use this to control different realizations and so on. Okay, this is just a recap. So we already played with this. When you have a parameter in a function and you want it to have default values, then you just use this equal to whatever the default value you want it to be. One other caveat is that the first several parameters that don't have default values, first several parameters without default values have to happen. That means if you have one parameter with no default value or two, they should happen before the parameters with default values are specified. This was like a lot of minutes of my time wasted not knowing this. Okay, so here's that's just a little function, simple example. So you can specify default values or not, and that'll just be the second one is default 0. You can also specify it this way. And this we can't because this is usually how methods are implemented with all default values. Then this will work, but because we require the first argument to have a user specified value, this will fail. So it takes at least one argument. Okay. This will also give an error again because X has no default value. Okay. Not sure if we covered this, but yeah, so Python has something called none. So none is of type none type. Python's none. So I mean, it's its own. So you should be aware of it, and it'll help with deciphering error messages as well. Yeah, so here's a little exercise. We'll try later. So if I say none, then the random seed is actually reset to a new random value. Right, so if you just look at this again with a none, it does this explicitly. Yeah, so it's just a bunch of exercises to reinforce concepts. So here is a simple simulation. I think this is definitely a way for you to show me you have understood or whatever. You know, if you're taking it for credits or something, then. You remember last week we had this little thing. I think Dan said he finished it immediately. What was the exercise, Dan?
Drunkards walk in 3D.
Yeah, drunkards walk in 3D.
Yeah.
Yeah. So did anyone else finish that?
Just in 2D. Yeah, in 2D.
Okay. Okay. Good. So I mean, I think you keep this as evidence that your plan works. This one's another good one as well because it mixes all these different little things. So what is a plan here? So there's kind of a simple simulation. So basically the buses are arriving at a bus stop with inter-arrival time in minutes of 10 minutes. So the rate is 1/10. So every 10 minutes on average buses arrive. Exponential distribution between arrivals. And then the bus has seats, 3 seats available on any bus, follows a de Moivre k = 40 distribution. So I don't know, maybe people get on and off at other stations or whatever, so there are sort of 40 seats. So when a bus arrives, it's sort of filled uniformly from this de Moivre thing. Seats are. And then you basically have to figure out how many seats are left, and then fill in the people that are waiting. And yeah, so everyone can, if there's more seats than people, then of course everyone can get onto the bus and nobody's left waiting. But if there are not enough spare seats, some people will be left behind. as they wait, more people arrive to join the queue. Yeah, of course, people are arriving at the bus stop at some rate as well. So it's not too bad, right? So you have two independent exponentials, and so then you have to keep track of how many people are waiting in the bus stop as time goes on. Yeah, it's not very realistic, but it actually has quite a bit of complexities of a basic queue. So you guys probably do queuing theory, right? In your business courses or OR courses?
No, not so much.
Okay. So anyway, here are the suggested steps. So these are, if you use these what do you call them, names, then it'll be easier for me to confirm. Check it out quickly. Okay, so that's a good U try. Oh, great. Yeah, I gave the whole answer. Yeah. Anyway, don't look at it. Yeah. Anyway, this is basically how the simulation will work. I mean, this is how one way of doing it, right? So you have, this is the number of people left waiting at the bus stop. And then we could do a little visualization of this. So this is the number of people boarding the bus as it arrives, and number of people waiting. And it's not actually, this idea, can now, honestly, it has all the elements to do fairly complicated things, including like Marina's world stuff. Because you see, we already have OpenStreetMaps, right? They've ingested them. We have, and there's something called open traffic. I couldn't get the APIs in time to get you guys. So you can actually download, world traffic data, opentraffic.io, because people are just volunteering their trajectories as they're moving in a guaranteed confidential way. And then that can be used to actually, unlike Google or Apple, like publicly keep track of where everyone, what the traffic is and in the road conditions. And then anyone can write an app to use that information to provide services, right? It's a pretty cool model. Have you guys been checking this? Let's do this. So, open traffic. Yeah. Global data platform. So, so this means, you can ingest this into our OpenStreetMaps of the particular city we are interested in. And then, you essentially can start keeping track of the flow information, right? Number of vehicles, speed, all of this stuff. And, that simulation is, you just think that there are kind of bus stops or, bottlenecks or whatever everywhere. And, it's the starting point. Is that your phone? Okay. So, yeah. So it looks like people are waiting, right, for a while. It's not enough buses. So, we can say, oh, well, we need more service here. And in fact, some nice little applications are like you can even do dynamic routing. I don't know what the traffic guys do. Is there anything like this, Marina? Like when you look at the actual waiting time of people and do public transportation authorities sort of dynamically do some kind of process?
Not when they look at bikes, which ones are free, which ones are not.
Yeah.
And there is one things that show like where they are and how long.
Yeah.
But in terms of how many people there to be.
Yeah. I guess it'll be better for Uber because I would be really pissed if like bus doesn't show up on a specific time it's supposed to show up because I'm just as important as the universe. I have an appointment, right? So I wouldn't like that probably for public transport because the schedules are useful, right? But I think for Uber or something like that, it makes more sense because then you can kind of have them swarm to where the people are waiting or whatever. Right? Because you don't want trains to like kind of start doing some gas with all the traffic. That's dangerous. That's what happens in India, but kind of, basically. In India, the whole country is a train. People, everything, cows, goats, they all have right of way, you know. In my city, yeah, cows and goats still have right of way everywhere. But they just build roads on top of roads for faster cars. Yeah, goats get up there now. So they eat the posters. There's a lot of cellulose. Anyway, that's a different universe. Here's hidden Cauchy running means. Oh yeah, this is the solution, I guess. Yeah. Okay, now let's get into the next notebook. So that was fine, right? Everything was here. We'll go kind of fairly fast pace with that today. So now we have a lot of concepts, right? Estimation, likelihood, maximum likelihood estimators, and then some symbolic expressions and Sage. Okay. So here's a bit of the outline. So we will talk about parameters in models and in real life. Well, parameters in mathematical models and mathematical models applied to real life problems. Then this very important idea called the likelihood, and this principle called the likelihood principle. I really want you to appreciate that that's a philosophy of operations and decision. But it seems to be pretty decent to because there's a high utility. It works a lot of the time, but it's not the only way to do decisions, right? And then so we'll get into the likelihood function for the Bernoulli theta random variable, and just look at the log likelihood function, and then that will be enough to define the maximum likelihood estimator. And the maximum likelihood estimator basically is going to take the data and then find a single best guess for the unknown parameter. Right? It's the inverse problem. And then we will get into this New Zealand lotto data. We're looking at the first ball number that pops out of this New Zealand lotto machine. And then a little excursion into basic algebra and calculus using symbolic library in Sage. And then we will get back into the New Zealand earthquakes, interoccurrence times. So how many of you continued playing around with the ingestion of earthquake stuff? Nobody?
During class.
Yeah. Yeah, I mean, so I did this list comprehension. Lee was not. She wanted to write float. So anyway, I kind of cleaned that up another 20 minutes or so. So we have a try-catched, float fielded list comprehension, and then. But the main thing is I spend a bit of time on timestamps, which I kind of dived into in Python. That took almost an hour. So timestamps are a pain, and this earthquake data has this timestamps in this format. So I will sort of give you guys pointers into how to deal with timestamps in Python. And then our main goal there is to extract that timestamp field, which is the occurrence time of earthquakes, convert it into a Unix integer long, which is the number of seconds since 1970, January 1st, midnight. And then we will use those integers, floating point representations of those integers as our main time information, so that we can find the difference between consecutive timestamps. Then we will just get the number of seconds between consecutive earthquakes. And then we'll see how well that can be modeled by exponential random variable we saw, just like waiting times buses. And surprisingly, this exponential guy, it's very, very, pops up a lot in sort of naturally observed patterns. Okay. Then we'll get into a bit into maximum likelihood principle, and then we'll do maximum likelihood estimation for this exponential random variable for this inter-earthquake times for New Zealand earthquakes. Okay. So estimation and likelihood, what is the big picture? So this is now moving into the second part, which is statistical inference. So we invert the probability model from the data. And then there's basically three main kinds of sort of attractions of, or main branches of likelihood applications, right? So one is in the world of point estimation. So point estimation is just a single best guess at some quantity of interest. You want to know what is the parameter of the exponential random variable that best fits the data. That's a single best guess for it. That's why it's called a point. Point estimates can actually be points in some space, which itself could be sets. So it's a bit complicated, right? So for example, I may be interested in, well, okay, it's gonna get crazy. So for example, a conversation that a sort of AI bot has, can be actually recast as a point estimation. Because you can recast its whole sequence of interactive whatever arguments it has as actually a point in some interactive dialogue space. So it's not just a real number, right? It's very general theory. But the set estimation is very different. What we mean here by set estimation is there is still a quantity of interest in some set, right? And let's say it's a set of points, or each element in the set we're calling a point. Then now set estimation means it's going to guess a set that traps the true quantity of interest, which still is a point, with a very high probability. So that's kind of the main idea of set estimation. Is that clear? So you find a random set that traps this thing of interest with a high probability, and that's set estimation. So usually you should have probably seen something called confidence intervals in 100 level statistics, right? That's the simplest example of a set estimation. Estimator. And then the third main branch is hypothesis testing, right? So this is very important, right, this particular branch, because now what it allows us to do is to attempt to reject falsifiable null hypotheses, right? So I briefly mentioned this before, but so I mean, I personally, one of the reasons I like statistics is that, what do you call this? So I mean, statistics is interesting because so it's sort of at the intersection of philosophy, law. I don't want to put Venn diagram. Okay, I don't know. So law, empirical sciences, empirical studies, whatever, science, engineering. So it's kind of, and it uses the language of mathematics, right, as a language. Yeah. So I mean, this is basically how stats sort of, and the first person that started a stats department in University College London is actually a physicist. He walked out of the physics department and did this. And there is some important history behind this. So around, late 1800s, this is an English perspective, people were, so-called scientists were always fighting with each other. They'll show their data in the whatever table, and they will say, look, this number, it's so big compared to this, and they will just basically psych each other, This is all explained nicely in the history of stats. So, it's like a mind game, like, like something like, managers do generally. I mean, no offense. But, so that's okay, in certain settings, but it's really not okay when you're doing science, right? Because it's just, that, your ability to psych your colleagues is not going to hold the bridge together, right? So it took actually a cultural change, right? And this is when Pearson starts writing this paper in Philosophical Magazine in 1901, right? And this is the birth of the chi-square distribution. So he does very elementary multivariate calculus. There's nothing super fancy going on. And Knuth's Art of Computer Programming has a full detailed proof of his. And what he was showing is, look, these numbers, these tables you're producing to say, like, whatever, there's some counts here. There's, blue eyes and whatever, black eyes. I don't know, blonde hair, brown hair, whatever. You some. If you're starting to make some correlation between, say, eye color and or IQ, let's say, there's a whole field, right? So some of this is really crazy. Oh yeah, and cranial size, actually. This is really interesting history. So the guys that did a lot of very basic stats, including Galton. Galton actually invented he's one of the fathers of this field called biometrics. And so when I was in UCL, my office was in the biometrics laboratory for eugenics or something. They really believed in, stuff, right? They didn't understand at the time that skin color is just actually a confluence of 5 complex traits, 5 complex locations in the genome. So they had their own biases, and there was a whole colonial enterprise on top, so they I don't know, they was doing all these weird, bizarre things. They're measuring the cranial size, and there's of course a correlation, but they're not accounting for the because different groups of humans have different packing densities of Swiss and gyri and neurons. So it's not just the cranial size; it's much more complex. But they had this whole theory, and they'll do these counts, and even with those counts, and possibly more currently pseudoscientific theories, they were not doing mathematics and statistics properly. That's what Pearson did all of this. Initial work, and of course a lot of people did a lot more. And so stats is in that sense very interesting, right? This is one important point. The second important point about stats, and everyone including Fisher and them, is Fisher also has a very strong background in physics, right? Physics and maths in England was really coupled at the time. And he was, he and others, in Russia, Dobzhansky, for example, they were interested in understanding why the world is different. Right? The standard physics question was trying to find a law that is common to everything, right? But now these guys are like saying, oh, look, the world is so different. We want to understand why it's different, the diversity of it. Right? And so that's why Fisher, in fact, did a lot of genetics, population genetic experiments on the coat color of mice in his house, right? He was doing hardcore theory. And that's, again, has been always a tradition, good statistical tradition is you do your own experiments as well, because that's when the insights flow. Kolmogorov did the same thing as well. So anyway, that's sort of high-level spiel. The sort of more low-level thing about hypothesis testing is this, right? So this is, I mentioned this already. So if this is the space of all possible hypotheses, so this is, you say whatever you want, right? Some entity made the universe, right? It could be whatever entity, depending on your, where, from Texas or Saudi Arabia or whatever, it doesn't matter. That's a hypothesis you're posing, right? Saying this is it. But the problem is, can I actually do an experiment, using pure empirical, stuff like I heat something or, just do an experiment that I can use to generate data and in an attempt to show what you're proposing is false, right? So if you say something that I cannot do an experiment to try to produce evidence against what you're saying, then what you're saying is not falsifiable. I cannot show it's false. So this is a very, very amazing idea of Popper, right? So Popper, philosopher of science, and so yeah, Karl Popper. So he actually came to Christchurch in New Zealand, when he escaped World War II. So what he says is there is a subset of possible hypotheses that are falsifiable. Right. And these are scientific. This is his definition of scientific hypotheses. So science, non-science. So this was an interesting problem in epistemology and philosophy at this time. This was called the demarcation problem. How do you demarcate or separate science from non-science? Yeah. So anyway, these links are useful to chase stuff. Likelihood also comes into everything we've seen in the big data course, including regression, multivariate regression, classification, random forest, ensemble, that's pretty much everything. Likelihood is under the hood. Even k-means, the likelihood is under the hood, right? Do you guys recall what is the probability model behind k-means? Yeah, so you have spherically symmetric Gaussian random variables giving you the cluster centers, right? And that's basically how you try to do the clustering, right? And what you're minimizing, when you put the, when you say, assign different memberships and then you change it back, what you're minimizing is actually the log likelihood function of the Gaussian, a mixture of k Gaussian random variables. Okay, so it's kind of everywhere, and of course Bayesians cannot even continue without likelihood. They usually take the likelihood function and then multiply it by some other distribution that encodes the prior beliefs or knowledge about the experiment. So yeah. So then there are two types of estimation. In this notebook, we're going to be looking at parametric estimation. The other kind is a non-parametric estimation, which we'll visit hopefully after, as soon as we can. Okay, so I don't know, real life sounds kind of too much. Yeah. Too much time to write all this. So anyway, here is George Edward Pelham box. So he said something that I think we should not forget. All mathematical models are wrong. Okay, but some are useful. This is super important, right? We are not like physicists or whatever scientists who think they're finding the truth of the world and reality. Let them do that. That's their own, however they use to drive themselves. No offense to physicists here. I mean, I don't really believe the world is 11-dimensional thing the string theorists believe, right? Dimension is a mental concept. So we definitely do this. This is a very natural statistical point of view, and there's nothing wrong with it. The other thing I want to emphasize is that the only maths I didn't use is the one I did not know. This is my favorite, one of my favorite statisticians. I never met him. He died at Berkeley before I met him. But he actually was very inspirational for a lot of work that Mikhail Nussbaum, one of my advisors, whose talk we will attend today, so that's part of the lecture, the colloquium. So he worked on this thing called account theory. So again, this emphasizes the point that maths is a language for us, And I guess, yeah, the third very, very important point, going back to what you were asking is, the statistical perspective is very unique in this other sense as well. Whether you believe this is from just the probabilistic perspective. So from the probabilistic perspective, a statistician typically is interested in, there's something happening, you're measuring something, and then, you usually, based on some measurements here, you usually do, there's something else called the action space, which is what we're getting into. One action is a hypothesis test. Another action is a parameter estimation. So you're always, trying to make a decision to take an action. Right? That's the usual setup. But what is super important is also to realize that to understand what is mathematizable, what is actually conceivable, executable, and to provide some kind of actionable intelligence using mathematics, and what remains. Okay, this is what remains in whatever the real world or whatever, right? So this is super important. So this is my little take on it. I say like omega is sacred, like Monty Python. Right? So all the little omegas are sacred, right? The tiny little omegas. It's very, very important. And that's what drives a mathematical statistical statistician, basically, because then you go and try and invent, new arithmetics or whatever you need, right? All right, now let's get into the likelihood function. So here's the basic idea. So the likelihood function is a function of the parameter theta, right? And it has this sort of n observations in it, and usually it's denoted by capital L sub n of theta. And so it's a mapping that goes from, so bold theta is now the parameter space where the little thetas live, right? You know, for the exponential, bold theta is just the positive half line, right? Because lambda, parameter lambda can be any number. So now, yeah, that's, and for the Bernoulli, theta is just the unit interval 0, 1, because it could be any number, any real number there. So now, what is the actual value? I mean, what is the actual expression for Ln? So for that, we have to consider the actual probability model, right? So we've only been looking at the simplest one, the IID model. We'll look at Markov chains soon. But in the IID model, what is the assumption? You have n observations, and they're independent and identically distributed according to the same density. Right? So if that's the model for your data, then the likelihood is defined like this. And so L sub n of theta is simply actually L sub n of x1 through xn semicolon theta. That's actually the real meaning. The x's are there in the likelihood, the observations. And then this is, yeah, being sloppy, I should say this is proportional to Theta over here, it'll probably be jumping. So this is not equal to by definition. So it's proportional to this thing. This thing should be proportional to. And then you know, I just, because of the IID model, right? Now is the only place where I'm using this IID assumption. I just multiply each xi's density. Because of the independence assumption. Otherwise, you have to go out right after the joint density itself, right? So this could apply to any model, absolutely any model, including artificially intelligent robot chatting and all this stuff. So here is the product for our case. Yeah, so basically the likelihood of the parameter is simply proportional to the joint density of the observation given that parameter. Okay. So it somehow tells us how likely is this observation for this parameter, right? So as we move around the parameter space, it'll tell you how likely the data is for that parameter. So the more likely it is, in this sort of philosophy, you kind of try to say, well, the most likely parameter is the best guess. And there's some justification for it as well. It's not just philosophy because I feel like it. So here's the likelihood function for the Bernoulli theta random variable. So let's sort of play with it to, yeah, and I just put a whole bunch of stuff. Fortunately, hiding cells is difficult, and so just hit that. And then there's this, there's a cell I want you to sort of quickly evaluate. So like this, and then try to close this. Oops. There. So I just evaluated it and hit it. So I don't want to get tempted. So there is some parameter there if you didn't look for the Bernoulli theta. So I'm going to pretend I don't know this parameter. I've simulated it. It's hidden from me. So now I'm going to go and take the samples and estimate it. And so that's what's being done here. So here's a sample. And then if I set up my Bernoulli, I just basically have theta to the x, 1 minus theta to the 1 minus x. That's the mass function. So to get my likelihood, I just have to get the joint mass, joint density for the data. And because it's just a mass function, I just multiply all the individual probability masses, right? So then this nicely comes in this form. So I have theta to the power of the number of ones, and 1 minus theta to the power of the number of zeros. That's all it breaks down to. So which means, the only real thing that has all the information about the data is the sum of xi's, right? The number of ones. Get sample size n and the number of ones. So then we usually summarize that as a statistic, because remember, statistic is a many-to-one mapping. So we don't need to know the exact sequence of ones and zeros under this IID Bernoulli model. All we need to know is how many ones happen and what's the total sample size. So we usually put that into this simple statistic Tn. So now the likelihood is only dependent on the data up to Tn, number of ones. And this is actually what's called a minimally sufficient statistic, because you cannot make it any simpler than Tn. Okay, just the number of ones. You need that information to understand data. Yeah, and usually you put this, so again, capital T here basically is the random, is the statistic as a random variable. That means every time you repeat the experiment, you'll get a different lowercase tn, right? Different number of ones. So this is just from before. So this is our sort of standard notation from before. So Tn of the data is simply sum of xi's, and it's going from the data space to the statistic space. So what is the actual value for Tn now? So what is the actual set for Tn?
The space, I mean.
Yeah.
It's from 0 to n.
Yes. Good. And integers?
Yeah.
Or real numbers? Okay, perfect. Very good. Okay, so let's, so I made this Bernoulli sample, right, upstairs, in this hidden thing. So let's take the sum. So it says there's 7 of it. So let's also make a little function for the likelihood of the Bernoulli, right? Do some little error checking, and then I'm simply implementing the likelihood for n observations, right? So I need my t statistic, theta and n. Oh, this is not like the t statistic in some classical statistics course, right? Okay, yeah. So we are using RR of theta because we really want to exploit the multi-precision floating point arithmetic now. You cannot do this as easily in a usual C library with doubles. It's a lot more into the field. Because when you take some small number and 0, 1 to a very, very, very large power, you're going to flow out, right? You're going to get into issues with the floating point screen. Okay, so here is a little U-Phi. I think, yeah, we'll probably skip this. Sorry. So let's just quickly go through this. If I have the Bernoulli sample 0 as just the tail, just the 0 event, then of course Tn is just 0 because there's no ones in it. And that's what I've sort of done here. And I'm looking at what is the likelihood for this when you just have one sample, just to get us going. And then if my theta is actually 1, then what is the likelihood again? So now this is 0. And when theta is half, what is my likelihood again? For the Bernoulli sample 0, right? Just one tail. You see it's 0.5. So that means, so depending on the value of theta, you're just going to have different likelihoods for the particular observations. So that's all this is doing. So if we observe 1, the likelihood of theta being 0 is 0, the likelihood of theta being 0.2 is 0.2, and so on. Right? Because now it just maps to theta. So now use list comprehension to get the likelihoods as well. And using a range, we can start making a little set of values for theta. And now let's say we have two samples, 0 and 1. And now Tn is 1, 0 plus 1. And then basically we can get our likelihoods now. It's kind of important to understand it like a bit slowly, I think. So we have one observation with x1 is 0, one observation where x1 is 1, and two observations where x1 is 0 and x2 is 1. This is the behavior of the likelihood function over theta. Okay. So, yeah, so I think here this is just the other possibilities, right? Or the other possibilities for two observations. What if x1 is 0 and x2 is 0, right? So this is, because this is 1 minus theta squared, right? Because that's the likelihood. This is what? Theta times 1 minus theta. This is also 1 minus theta times theta. And then this one is theta squared, right? You following it? It's just these guys are battling, right? So who are the guys that are battling? It's these guys, right? It's like this sort of multiplication sword fights, right? That's all that's going on. It's kind of really simple. Okay, so let's see what this interact does. Oh yeah, so it just lets you play with this now. So you can change the sample size. And this is that secret theta that we have. So we supposedly don't know what it is. And we're increasing the sample size, and look what's happening. The likelihood is concentrating around, it looks like around 0.3, right?
Yeah.
Yeah, so I would guess like something is going on around 0.3. I mean, this is the justification. This is the justification for the likelihood principle, the maximum likelihood estimator, because this bias in the coin is going to come by simply repeating the experiment, and that's the whole point of science, to be able to do controlled experiments you can repeat. So the multiplication brings all the symmetry because of independence, and then we can learn the parameter by inverting the likelihood. That's the idea. So the next main concept is logarithm of the likelihood function, because directly leading the likelihood function is a bit tricky. We can do it with multi-precision arithmetic up to a certain point, but it gets slower and slower. So logarithm is great because it's a monotone function. So if you're interested in finding the maximum value of this likelihood function, remember it was concentrating around 0.3. So we may want to hunt the parameter that maximizes the likelihood function. That could be numerically unstable, or even like mathematically harder to track. Because log has this nice property that log of a times b is log of a plus log of b, we can take these product expressions and turn them into sums of logarithms of the individual densities, right? So that's the main idea for log. And then because log has a monotone property, we can basically I think we'll come back to that in a minute. So it preserves the maximum, the arg max. So let's just, this is basically how you would play with log. And usually log is base e. Yeah, defaults to base e. If you want log with other bases, you just put a comma 10, because that's the default parameter is e base. Okay, so yeah, that's essentially our nice property of logarithm. So now we use lowercase l sub n for the log likelihood function, and uppercase ln was for the likelihood function. So we simply have, we just take logarithm of likelihood function, and log goes inside the multiplication as sum. Okay. So just marching through for the logarithm of the likelihood function for the Bernoulli random variable, Bernoulli theta random variable, and this just, properties of logarithm.
Is this log of the likelihood function also called entropy?
No, entropy is a different thing. Yeah. Let's not go there. I don't want distractions today because we really have a military schedule. Like we need to get to some basics. But you can look up entropy. It's a different idea. It's based on the density of the random variable and the logarithm, but it's not the same. Okay, so yeah, so this is just explaining some high school maths of how that works, right? So now logarithm is a monotone function, right? So that means it's non-decreasing. It's So this is what it means. So if A is less than or equal to B, then f of A is less than or equal to f of B, right? Because it's like this, right? So no matter where I go, I take two things, where x is less than y, then f of x is always going to be less than f of y, right? So because of the property, if I have some other function, some other function f, the density I'm really interested in, right? And maybe let's say it's even completely multimodal, who knows, some very complicated density of the data, joint density of the data. Then when I take the logarithm of it, if this is the argmax, for this f of x, then log of f of x, it'll still be the argmax of logarithm of f of x because of monotonicity. So that's nice because then we can sort of take logarithms and still hunt for the maximum likelihood estimators using log of the likelihood function. So that's all that is, and this is just some other interact. Yeah, so this is just showing you the likelihood function and how the log of the likelihood function looks for just our twos, one head, one tail, I think, DNS1. And yeah, so as we keep increasing the sample size, I mean, if you look at the plot, it's a bit hard, but yeah, it's exactly at 0.3, they're both maximizing. Okay. Now, here's a bit more about maximum likelihood estimators. So in fact, actually, this is the definition. So we put a hat on the parameter, and now the parameter theta itself is capital theta, right? Just in the usual tradition, we have lowercase theta for a deterministic point, right? Or just like lowercase x is an actual realization of a random variable capital X. Now capital theta is actually a random variable. Okay, it has some density on the space where little thetas live, right? And then bold theta we saw is the space where theta lives, right? And then now capital theta with a hat on it is, so whenever you put a hat on some capital thing, it means it's an estimator, right? It's a random variable whose job is to estimate something you're after, right? And this is a point estimator, so it'll look at some data and then throw, it's called a Markov kernel, it'll throw a point in the data space. And every time you redo the experiment, it'll throw the point in a slightly different space. So it's a point estimator. And you put a hat because, yeah, that's the tradition. So here is the definition. So theta and hat is actually a function of these random variables, the n of observations. And it's defined as the argmax, which means the argument that maximizes this likelihood function. Okay? And the argument ranges over, this is bold theta, it ranges over bold theta, little theta. Right? So it was 0.3 in our world because that's where the likelihood function peaked for our interactive level. And because of the monotonicity, it's also the argmax of the logarithm, log likelihood function. So they're the same. Okay. Yeah. So then the question is, how do we actually find this? Suppose we have an expression, we have a model for the data, and then we look at the joint density of the data and find something proportional to the joint density. We have a likelihood to take the logarithm of it. All right, so now what? How do we actually find the argument that maximizes this log likelihood function? Well, for simple cases, like we'll play around here, and in the process we learn about symbolic expressions in Sage, we can directly go after it, right? We can just try and solve it using basic, by hand, or symbolically if you're very rusty, right? And the other way is to do local optimization, and this is in fact all we really did in these big data modules, right? So you had some gradient descent algorithm that's sort of basically doing some heuristic way of looking at parts of the data because the data is too big, and it's actually looking at the likelihood function of parts of the data in these batches, and then when all the different batches are done, it's called an epoch, and we did some kind of walk, we solved this, right? That's a numerical way of finding the Argmax of the log likelihood function. Or there could be other methods, like K-means has his own weird heuristic method, which will not it's not guaranteed to find. None of them are guaranteed to find the optimal, the global optimum. But that's a different problem. Okay, so usually you do it exactly like this. So if you do it exactly, what are you after? You're trying to find the value where the derivative of the log likelihood function with respect to theta is 0. Because that's where the, so if I look at what is the derivative, so basically I have to look at what is the slope of the tangent at this point. So it's positive, 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 and then it comes to this place where, it slowly becomes flat like this, so this is 0 slope, right? So we're hunting for, and so this is given by the derivative, right? d by dx of L sub n of theta, or d by d theta of L sub n of theta. Right? So this is my log likelihood function, let's say. And so I want to find out where this is. And, I'm not too worried. Of course, technically I have to be worried like this. I will also find places where it dips to have 0 slope. So I usually have to make sure that the second derivative is positive, right? Yeah. How do I make sure it's
Negative.
Negative.
No. Minus.
So the rate of change, if the rate of change should be positive.
If you want the
Negative.
maximum,
Negative, sorry.
you want the derivative to be
Yeah.
decreasing, right?
Yeah,
So the second derivative should be negative.
yeah. Okay, down, right. Yeah. Yes. Okay. Good. Yeah. Anyway, yeah, this is just stuff. I mean, so in the end, what's happening is, you're basically finding that, when you set this equal to 0 and solve for it, you're getting that theta sub n hat is just the sample mean. Right? All this hard work. So, that's okay. And for other problems, the exact mechanics will lead to other expressions involving size. Now let's look at another version of the interactive plot. See what happens here. So here I'm just, this is the same. So I'm getting my MLE at 0.276. So this is again the secret data we're trying to pretend that we don't know, right? Well, pretending we don't know. We just have samples from it. And I'm increasing the sample size. And my maximum likelihood is getting closer and closer to, looks like it is getting closer and closer to 0.3. Right? So, look at that. So that's what my best guess would be. Right? Okay, so let's briefly get back into this New Zealand Lotto data. Remember, this is just the number of the first ball, and there's 1,114 of them. And I'm now interested in just the odd balls. So I just do this list comprehension, and now I get the Bernoulli 1 odd balls. So there's actually 546 of the 1114 are odd. And I can do, you know, we saw this, I can use this count method to find how many there are. So here's my, so that's already my statistics. So I'm basically going to use the Bernoulli model for whether the ball is odd or even. And this is now real world data. So I'm going to go and estimate the unknown Bernoulli parameter, which we call theta star, right? So we usually put a star when we are, you know, using a model, and then we are saying the true parameter under the model is theta star, and then we're trying to find it with theta hat estimator. So that's the main idea, and then if we work out the log likelihood for the Bernoulli and maximize it, we saw it's just the sample mean. So here I'm just creating a cumulative sum just to see how, yeah, so there's some types to be aware of. So I'm making the sample size sequence of sample sizes, and then I'm simply creating my relative frequency of the cumulative sums of the Bernoulli oddball data, and just plotting it. So what is this? This is actually my estimator for the unknown theta star, you know, in the Bernoulli model for the oddball popping out. And as you see, it's converging kind of to 0.5, so which is what you would expect from a lotto machine. It's a ball, each of the 40 balls is supposed to pop up, and there's 20 odd and 20 even. Okay, so now what we've done is we have sort of done as a simulation where we pretend that this secret theta we didn't know was set to 0.3, and then we did our estimation and simulation and everything, and then we're applying it to real world data. This is the typical thing you would do in any decision procedure. You would do simulations. In fact, when you're a data scientist and you make a pitch to someone trying to sell you stuff, give you money, you will do some kind of you know, early work to demonstrate proof of concept or whatever. And this is pretty much exhaustive, right? Because you're simply doing full simulations to show everything will work. And often you want to do this to test your code is working correctly as well. Okay, so let's see what this interact is. You should have coffee over there. Okay, so we have coffee in 4 minutes. I don't know, my fingers are hurting. I was typing like madman. I almost fell asleep this morning. So I don't even know what this does. Let's see. Oh yeah, so it's just the likelihood function based on first sample, and yeah, it's for this this data set. Yeah, this is pretty quickly converging, right? 2.5. It's pretty amazing. Yeah. The Brazilian lotto machine is not free. Okay, so this is again the same thing. We're just looking at logs, likelihoods. Okay. So here is another one where we're sort of looking at the log likelihoods again in different views. So that one will take a while. Yeah. So you know, just notice that as your sample size increases, we're just going further and further down, right? Because the amount of observations is very, very high. So you're summing a lot of you know, logarithms of densities, which are going to be negative numbers. So you're adding more and more negative numbers. This is again a common misconception. So you know, yeah. So when you have fixed number of data, you need to look at the curve for that fixed number of data and find the argmax at that curve. Okay, so should we take a break and then come back to algebra?
Sure.
Yeah.
Right.